So there's 3 steps in vibration predictive maintenance program. They are detection, analysis, and correction. The first step is simply measuring and trending vibration levels at marked locations at predetermined time intervals. Let's hear from Paul about selecting the frequency of time in between measurements.
Obviously, you only have so much time in the day to look at this stuff. When I worked at Irving Paper, I was responsible for 15,000 vibration points a month. So I don't have time to do a deep analysis on every single point when I'm doing the vibration analysis. So what I have to do is assign a criticality to each piece of equipment. So if it's a piece of equipment that doesn't really have any impact on the running of the mill, for instance, like we used to use an example of a city water pump when I worked at Irving Paper. City water pump, if it goes down, it's not going to really affect the mill. Your toilet might not flush, but it doesn't affect the mill. So we would only look at that piece of equipment maybe once every 6 months. Other pieces of equipment in the mill that would have an impact on the running of the mill, then we would increase the frequency that we would look at those pieces of equipment. So most pieces of equipment we would look at monthly. But super critical pieces of equipment in the mill, any piece of equipment in the mill that would put the mill down, if that piece of equipment went down and it put the mill down, stop production, then we would look at that piece of equipment once a week. So we would designate that equipment as, we called it red line equipment. And so we would set up routes with red line equipment where we would look at those pieces of equipment once a week, or some pieces of equipment that were extremely critical, we would look at them 3 times a week. That's probably the first thing that when you start your program is to look at all the equipment in your program and designate a criticality to that piece of equipment. So the more critical that equipment is to your operation, the more frequently you look at it.
It's an important distinction when discussing the maintenance program. Not all equipment is equally important to production. There's also cost of repair and many other factors which can go into this. So we have our machine list and we know the importance of each one relative to production. Now we need to actually measure the equipment vibration. How do we do it?
We would use a vibration analyzer. And so what that analyzer would do is when we take a reading on the piece of equipment, it would take all the vibration from that piece of equipment from all sources into the analyzer, and then the analyzer would perform a mathematical computation on that information, and it would separate it all out into different waveforms, as we talk about, and we'll probably talk about this later in the course. Waveforms that would separate all the sources into individual sources, and then we would look at each source of vibration and then determine whether that's detrimental to the machine, whether it's acceptable level of vibration, whatever we have. What you have to do once you get the equipment is you have to build every single piece of equipment in that system. So what you have to do, for instance, if you have a motor, then what you have to do is you have to take that motor and build a motor. So you have to tell the equipment what you're looking at, then you have to look at the bearings in that equipment. And so with that equipment, they all have different types of bearings. So we look at what the drive end bearing is, put that in the drive end each bearing. And each part of the bearing throws off a different signature of vibration. So you have to tell the machine what you're looking. So if you went to the drive end of the pump and it had a 6213 SKF bearing in it, you had to tell the system what bearing it was. And then it would have in its warehouse, it would have all the frequencies, and it would download that from the software into the machine. So we would have to tell it what type of bearings were in the machine. And then what's really critical with vibration was we also had to tell what the running speed of that piece of equipment is. If you don't have the running or the turning speed or the RPM of that motor, you can't calculate out anything else in that vibration. So you have to tell the equipment what type of bearing it is, what speed that equipment's running at, and then pretty much the computer or the software looks after everything else. So what you have to do is build every piece of machinery individually, and then when you go make a route, as we call it in vibration, a route is just a set of readings that we will take. And then what you do is you go into the warehouse, and every piece of equipment's built in the warehouse. And then so you grab this pump, you grab this gearbox, you grab this motor, and you put them all together in the software. You tell it how it's coupled together, whether it's a flexible coupling, whether it's a grid coupling, whatever type of coupling it is. Put all that information into the system, and then the box knows this stuff. Then you assign as points or the way that you want to take your readings, because what you want to do when you're out taking readings is you want to save as many steps as possible. You don't want to go take a reading on this pump here and then go walk a half a mile down to take another reading on a pump and then walk back. You want everything in order as you go along. So you set up this piece of equipment, you give it a label, so 23L24 or whatever, you give it an electrical number, you assign to that piece of equipment, and then you assign certain points. So the outboard side of that motor would be position 1, and you would tell what bearings in that position, what speed it's running at, position 2, position 3, position 4, however many positions are on the machine. We'll talk about that in a later lesson. And then make sure that you have the route set up in an order so that as you walk by the pieces of equipment, they're there, instead of, so as few steps as possible. You only have so much time to take the readings, and so you want to set up. Another critical thing when you're taking routes is that sometimes you'll have a pump and a pump and a pump. So you take a reading on this pump is down, it's not running. So you go on and take a reading on this pump, but you forget to advance the box to the next piece of equipment, or so instead of skipping this one, you're thinking you're taking a reading on this pump, but you're actually taking a reading on this pump. So when you get to the end of the route, you have 2 or 3 points left over. Which ones did you miss over the last hour and a half that you've been walking around? You don't know. So all that work that you've done is just, you wasted all your time. You got to go back to the start of the route and start again. So every time when I went to a piece of equipment, I would look at the electrical number on my box, 23L24. I would look at the tag on the piece of equipment, 23L24. Okay, I'm at the right piece of equipment. I would take the reading, advance to the next one, take the reading. Because I'll tell you, after you've been out there for an hour and a half in 120-degree heat, 100% humidity, and you get back to your office and you got to do it again, it's not good. We're not happy when that happens. And I have done it. So the reason I know all these mistakes is because I've made every single one of them throughout the years. So.
We have our machines entered into the vibration software, and we know how often each machine should be measured. I'm curious to know what a day in the life of a vibration tech looks like.
So generally what we would do is we would have most readings we would take would be on a 4-week cycle or once a month. So what we would have is every week we would have all the pieces of equipment that are due that week. So we would have that either in the software on our computer, or a lot of times we would just have a sheet of paper with the 4 weeks and all the pieces of equipment, and then we do those pieces of equipment that are in that week. So we come in the morning, okay, it's Monday morning, we look at, okay, this week we're responsible for all this equipment, and so we may not take the reading on the equipment on the same day every month, but we take the readings within the same week. And it's very, very critical when you're trending a piece of equipment. Everybody knows what a trend is. So we take a reading, and we take a reading a month later, and we take a reading a month later, and we take a reading a month later. We have to take that. Consistency is key in vibration. Using the same equipment, taking the readings at the same locations at the same interval of time. So consistency, consistency, consistency. What happens if you miss a month? Okay, you miss a month, and now you take another reading in 2 months, and the vibration is up quite a bit. Did the vibration jump up immediately, or was it a little bit higher the month before? So it can skew your trends if you don't take the readings at the same interval of time every single time. So very, very important. Consistency, consistency, the same location. And just another aside is when we take a reading with our accelerometer, we want to take the reading on that piece of equipment at the exact same location every single time. So the first person that does a route, what they'll do is they'll go out with an ink marker, and wherever they take the reading, they'll put a circle with an X through it like that. So the next guy, we had 4 people in our department, so I wasn't always taking the same reading every single month. So when the next guy went out and took the reading next month, you know exactly where I took my reading. So it was exactly the same single place every time. Consistent. Consistency is key.
When taking measurements on your route, today's equipment will alarm if the severity of vibration is high. But normally, the vibration severity has a very slow change. The question I have is, at what point does the rate of change prompt some sort of action?
Faults can develop in vibration over a long period of time. So like a bearing, for instance, I may detect that bearing in the very early stages, and before we actually have to change that bearing out, it may be a year and a half away. So gradual change over time. Other things will be a very sudden change. If you think of a fan, and we have a fan, it's turning, and all of a sudden something falls off, a weight falls off of that fan, or a blade falls off of the fan, what's going to happen is the vibration is going to change really quickly. So we look at the trend. So on a bearing, a fault, it may look like this. In the early stages, very low vibration, comes up very, very slowly. So we see the change and over a period of time, and then we decide when we should make the change. Other things, we would see a trend where it's exactly the same, 3 months, 4 months. In the 5th month, we take a reading, so there's a very sudden change. So why was there this sudden change? So generally, if there's a sudden change like that, something is broken off that piece of equipment. So you have a fan blade broke off, a balance weight on your fan is broken off, an impeller cracked or something like that, or so that would make a very quick change. And then a bearing, which takes a long, some bearings are faster than others depending on the load that they're under, the speed that they're under, how they're lubricated. All these things all play into how fast a fault will develop. And so what we look for in vibration basically is change. So if there's no change, if I look at my trend, the next month there's no change, no problem, I don't investigate. When I see this change, I have to investigate this. It may or may not be a mechanical problem. I have to investigate it to find out. This fan thing, for instance, maybe a weight fell off the fan, but it also could be a production type of thing where the fan is throttled, or the flow of air is restricted through that fan somehow, or the way the valves are set on that, or the way the fan is louvered or whatever, could cause a vibration increase. So I have to investigate to see if it's a process change. It's a process change. They change the process, the vibration goes away. If it's a mechanical fault, the vibration doesn't go away when you change the parameter. The critical pieces of equipment, and I'm talking critical as we talked earlier, the red line equipment, a lot of those pieces of equipment have online monitoring because we want to look at that piece of equipment all the time. Another thing with online monitoring, what it allows us to do is set alarm limits. And so with the online monitoring, what we'll have is we'll have a warning line, caution line, and a danger line. And generally the way we set this alarming up is that we'll talk later about baselining a system. Baseline is just the first reading you take on a piece of equipment when it's newly installed. We assume that that piece of equipment is pristine because it's just been overhauled, it's just been put into service, it's been aligned properly, it's been balanced properly. We take a baseline reading, and then what we do is we look for change from that baseline. 2 times the baseline, warning. 4 times the baseline, caution. 6 times the baseline, danger. And so what we'll look is our trend, and if we see our trend jump way up to here, 6 times, danger, 4 times. And so also what the online monitoring system does is that you don't have to leave your office to go take readings. You can look at that piece of equipment anytime you want. So if somebody, so you come in the morning, you look at the change, see the vibrations way up, I can instantaneously take a reading on my online system, because the thing with an online system is we put the accelerometers, we bolt them on the machine, and then we wire them right back to the office so we can look at that piece of equipment anytime. So we see a huge change like this, I can immediately take a reading. If the trend drops back down, it was something to do with the process. If it stays up for consecutive readings, then I have a problem. Generally what we do with an online system is the online system is the indicator of change. And then once we see something, then we'll take our manual system and go out and take our readings and do our analysis with the manual system. The online monitoring system just tells us if there's change.
So the rate of change is important. Sometimes operators can mishandle the equipment and damage components, or something can come loose suddenly. You'll see a large uptick in the severity of vibration, and the life of the machine has been drastically reduced. However, if you keep your eye on it, they can actually run for quite a long time at the high vibration levels with very little change. We just shorten the period between measurements and fix it when we can. We have meticulously collected the data, tons of it, at a very fine resolution. The next step is to identify the specific problems for scheduled maintenance. This is essentially the purpose of vibration analysis, to pinpoint specific machinery problems by revealing their unique vibration characteristics, or they're also known as their vibration signature. Some of the things we could pinpoint to are unbalance, misalignment, looseness, bearing defects, resonance, eccentricity, worn gears, motor electrical problems, drive belt problems, distortion from soffit or pipe strain. Let's hear from Paul what that process of filtering through the data looks like.
So a lot of vibration for faults is basically we're trying to recognize patterns. So an outer race on a bearing will make a particular pattern. So here's our spectrum. Of course, along the bottom is frequency on our spectrum. On the side is amplitude, how severe the vibration is. And so what we're looking for is certain patterns in the spectrum. So an outer race pattern will be a peak like this, which will be at the fundamental frequency of the outer race of the bearing, the inner race of the bearing, whatever. And then you'll see a pattern. So outer race basically looks like this. First fundamental frequency is high vibration, the second a little lower, the third a little lower again. If we had an inner race of a bearing going bad, just the opposite, fundamental frequency, okay? So inner race, outer race pattern, imbalance, 1 times vibration, misalignment, pattern 2 times vibration. So there's all different patterns that we look for. So what we do is we go out and take our readings, and then the analyst, generally there's different levels of vibration. So at level 1, basically what you're doing is you're going out and collecting the data, and then somebody else analyzes the data for you, a level 2 or a level 3 or a level 4, depending on how much experience they have. So generally, in my experience, is that I would collect the data, but I would also analyze the data. So I'd spend an hour or 2 going out collecting the data, come back to my office, and I would look at every single point. Every reading that I took, if this was the outboard side of the motor, the 1H position, would have a picture. 2H would have a picture, so I would look at each one of them. So what I would do is I would look at the pattern. So I would have this reading, then I would have my last reading underneath it. So here's another spectrum, and maybe the reading before. So I'd have my last 3 readings. I would look for change. So a little less, so the amplitude is growing each time, so I can see change there. Also, I look at the trend. It's up. So something's changed in that from my last reading. Something's changed. Why did it change? So now when I do my analysis, when I look at it, I look at for change in the trend, I look for change in the spectrum, and also the waveform. I look at the last 3 waveforms, and I can check and see if there's more amplitude, if there's more vibration over a period of time. And then what I'm doing is trying to recognize the patterns. And in order to do that, it's not something that you pick up in one day, okay? This is thousands and thousands and thousands of spectrums that I looked at over time in order to get this pattern recognition. But the thing is that once you have it, basically I'm looking at each point for maybe 10, 15 seconds. If I don't see any change, move on to the next point. If I see change, why did it change? Was it a process related issue? Is it a mechanical issue? Once I determine if it's a mechanical issue, how severe is that? So not only do we detect the change, assign a fault to this, so for instance we had a bearing fault, but also how long that piece of equipment will last before it fails. And so the reason we do that is so that we can plan our maintenance work. So I can give the maintenance department heads up, say, hey, this bearing's gonna go in 2 months. So we don't need to shut next Wednesday. We don't need to work on this bearing because it's going to last for 2 more months. So it allows us to focus our maintenance activities on things that need to be done now. We're not, so we're just picking off what we need to do now. Anything that can last longer, we put off to the next shot. So it makes it more economical, and it's just a better management of our resources, because we can predict when things are going to fail. What we do is we eliminate the things that break down in the middle of the night where we have no time to plan, we don't have any manpower, we don't have any equipment. So it gives us time, gives us a head up, gives us leeway for our job. So that's what the whole deal is with vibration analysis, is find the fault, analyze the fault, and then make a recommendation on how long that thing will last before it's going to fail. So it's basically the job.
Once a vibration signature has been analyzed, the vibration tech would make recommendations in a report to the maintenance planners and production staff. I asked Paul to talk about what it's like to communicate some of those machine problems.
And that's the thing about vibration analysis when you're a vibe person, is you can't take this stuff personally. Okay, you make a recommendation, but you also cover your butt and you write down and document every single thing that you do. So every person, if you tell somebody there's a fault, when did you tell them? What did you tell them? What day did you tell them? What time did you tell them? Because what's going to happen is sometimes there's going to be a breakdown and they're going to look for somebody to blame. And they're going to blame the guy at the bottom of the hill, and you're the guy at the bottom of the hill. So cover your ass, okay? Make sure that you document every single thing. And then also, you can't take it personally, because I worked in the paper industry. And for instance, here, Easter's coming up. So it's one of the busiest times in the paper business. Maybe they don't have time to take that piece of equipment down. They have orders that they need to fill, so they don't have time to do the maintenance. So what they'll do is they'll gamble. And they'll say, well, maybe we could put this off a little longer. Sometimes you win, sometimes you lose, you never know. So just make sure that when they come back and say, why didn't you tell me about this? You can open up your little journal and say, well, I did tell you on January 10th at 11:10 in the morning that you had an outer race defect on the outboard side of that pump. And it was in the first stage of bearing failure, and I told you how long it was going to last. So basically, but like I said, they're not going to be hanging on your every word. I can tell you that, okay? Because the thing about vibration, the thing that we have to realize is every time you go to your supervisor, you're a problem, right? Every time you go, you're not going to tell them good news. You're not going to tell them great things. You're going in there with the problem to tell them that he has a piece of equipment that he has to deal with. So every time they see you coming, they know it's not good news, or you wouldn't be going into their office, right? So a lot of times, what I would do, if you like to mess with them a little bit, is I would just take a little piece of paper and I would walk around the office suite on Friday afternoon, and everybody would look and see me coming, and then they'd shut their door, or they'd leave, or they'd go someplace because nobody wants to talk to you. And anyway, I used to do that just to mess with them every once in a while, just to keep them on their toes.
It doesn't matter what the application is. Predictive maintenance, quality control, field service, whatever. Vibration detection and analysis to plan and correct machine fault condition works. To do it, you need the right equipment, but you also need the right people, like Paul, to use the equipment properly and effectively. Paul didn't walk into vibration at the start of his career. He started machining and worked many years as a millwright before he began in vibration. That experience gave him the depth of knowledge of common machine problems of the machines and how to correct them. Over 17 years, he fine-tuned his ability to read the vibration signatures and data trends to pinpoint mechanical faults and or operational problems.